Okay, guys, welcome. So this is a continuation of the first part of section 2.2 on quadratic functions and conics. We're now going to talk about the conics part of this lesson. Okay, so picking up with where we left off, we can now talk about what we mean when we have the equation of a circle. All right, so if the center is h comma k, so some ordered pair h comma k, and the radius is r, then we can write that the circle equation is given by x minus h squared plus y minus k squared equals r squared. All right, so let's look at a couple of examples. So first we wanted to find an equation that describes circle with radius 3. So radius 3, of course, tells us that r is equal to 3. And it's centered at the origin. Well, where is the origin? It's 0, 0. So now our formula for the equation of a circle is x minus h squared plus y minus k squared equals r squared. And again, remember that your center is h comma k. So if we plug everything in here, I should just be plugging in for h, k, and r. Right, so that's sort of the shell of what we want to work with. Well, my h coordinate is 0, my k coordinate is 0, and my r is 3. So if I simplify this, x minus 0 is just x, so this part is x squared. Y minus 0 is just y squared, and 3 squared is 9. So the equation of the circle centered at the origin with radius 3 is x squared plus y squared equals 9. And of course, if you wanted to see this on a graph, sort of just a rough sketch here, you'd have something like that. Its center is at 3, and it has a radius. Sorry, it's centered at the origin and has a radius 3. Okay, let's look at another example. So same idea. We're centered at 2, 1, which again is like h comma k, and our radius is 5, so that's r equals 5. So plugging into the formula, we should get x minus h, so minus 2 squared, plus y minus k, so y minus 1 squared, is equal to 5 squared. Now, the only thing we can really do, you don't want to FOIL this out because then you're going to, it's going to be a little bit harder to see what this is describing. But if you want, you can square the 5 to give 25, right? So that's fine. All right, so that's the equation of the circle centered at 2, 1 with radius 5. Now let's look at a more complicated example. So now we want to find the radius and center of the circle. So now we're sort of going in the opposite direction that's described by this equation, this x squared, plus 4x plus y squared minus 6y is equal to 12. Now, if you're following along and you want to try this on your own, the idea is that you want to complete the square for both x and y, and then that's going to allow you to come up with this equation. Okay, so let's see what I mean by that. So if we look at what we have here, we have x squared plus 4x, I'm going to leave myself a little bit of room, plus y squared minus 6y, leave myself some room, is equal to 12. Now, the idea is that we want to be able to write this as x minus something squared plus y minus something squared equals something squared. Now, I don't have something squared for my x or for my y, but we talked about how we can make that happen, right? We just need to complete the square. So in this case, in the x version, my b is 4. Okay, so if I take b over 2, that's 2. And if I square b over 2, that's 4. So I need to add 4 in here. But since I added 4 to this one, I need to add 4 to this right side as well. Okay, now for the y version, I need to also complete the square. So in this case, my b is -6. My b over 2 is -3. And my b over 2 squared would be -3 squared, which is a +9. So I need to add +9 to both sides. Well, now we want to simplify all this junk. All right, so if we copy and paste this, all right, we want to now factor each of these, and we'll have something squared, right? So this again factors into x plus b over 2 squared. So this is going to be an x plus 2 squared. And this part is going to factor as y plus b over 2 squared. And since this is a y plus a -3, then we'll just say this is y minus 3 squared. And then, of course, that right side will be 12 plus 4 plus 9. And if we add all them, we'll get a 25. Okay, so now your center, we can see clearly the center is the x value is -2, right? In order to fit the formula, we need -2 there. So it's x minus a -2. And my y coordinate is 3. And of course, the radius is the square root of this thing. So the radius is 5. All right, so that's our center and radius for this example. So occasionally you may need to complete the square for this. Okay. Now, once you talk about an ellipse, or sorry, once you talk about a circle, you can modify that slightly, and then you can then talk about what's called an ellipse. So if you were to take a circle and stretch it either horizontally or vertically, what you then get is sort of an oval shape, which we mathematically refer to as an ellipse. All right, and sort of if we write it in this form, what we can think of is that if we take a circle of radius 1 centered at the origin and stretch it horizontally by a factor of a or vertically by a factor of b, what's going to happen is we get an equation of this form. Okay, and then of course you can get that those 4 points would be on your ellipse. You get a comma 0, you get -a comma 0, and 0 comma b, and 0 -b. Okay, so first, in this first example, we want to find the equation for the ellipse that's produced by stretching a circle with radius 1 centered at the origin, so we know it fits this formula. So it's horizontally by a factor of 5. And it's being stretched vertically by a factor of 3. All right. Now what happens here is that if you look at what we have before, the horizontal stretch is being associated with the x term. So we can call that our a. So this tells us that a is equal to 5. And of course, by process of elimination, the vertical shift, or vertical stretch, I should say, will affect the b term. So if we had an equation x squared over a squared plus y squared over b squared equals 1, then this particular ellipse would be x squared over 25 plus y squared over 9 is equal to 1. So that's what this ellipse would look like. All right. What we can now talk about is what's called the foci of an ellipse. All right. So these are 2 points that if you add the sum of the distances from each of the 2 foci points to a different point on the ellipse, that will always be the same constant, all right, regardless of which point you choose. Okay, so to find the foci of the ellipse, you get these 2 points here. Basically, you're finding a squared minus b squared and taking a square root, and you're going to use the plus and minus version of that for your x coordinate. And if your b coordinate is bigger, it's now in the y coordinate, and you just change the order. All right. So for example, let's look at, so for part A here, we want to find a formula in terms of x for the distance from a typical point x, y on the ellipse, x squared over 25. So the ellipse we just found, y squared over 9 equals 1. Okay, to the point 4, 0. So of course, first of all, we need to find what the 2 foci are. All right. So in this case, A is bigger than B. So we're going to have that our 2 points will be a squared minus b squared, square root, 0, and negative a squared minus b squared, 0. So if we find square root of a squared minus b squared here, we're going to get a 25 minus 9, which is square root of 16, which is, of course, plus or minus 4. So we're going to get that the 2 foci are 4, 0 and negative 4, 0. Okay. So, of course, this is our one of our foci points, and of course, this is the one that you're seeing in part B. Okay, now if we wanted to find the distance for any arbitrary point to either one of these foci, so I actually sort of did part C first here. This is really part C. Now, if we want to find the distance for each one of these, if I have a point xy, then the distance between xy and 4, 0 would be x minus 4 squared plus y minus 0 squared, which is just x minus 4 squared plus y squared, square root of that. And of course, in part B, it's similar, only now you're going to get minus a negative 4 squared plus y minus 0 squared. So this would be square root of x plus 4 squared plus y squared. All right, so that's giving the distance from 4, 0 and negative 4, 0 to any point on the ellipse. All right, and then in part, the first thing I did, which actually ended up being part C, we showed that there are the foci for the ellipse. Okay, one last thing in this section that we'll talk about is what's called a hyperbola. And that, so a hyperbola is if you have something like y squared minus x squared over a squared, and then that just equal to some arbitrary constant c. All right, now what does a hyperbola look like? It looks something sort of like this. All right, so this is a basic example of a hyperbola. So it's a wacky looking shape, something like that. Okay, but anyway, so in example 14, we want to explain why points x comma y on the hyperbola y squared over 16 minus x squared over 9 equals 1 for large values of x and y are near the line y equals 4 over 3x or the line y equals negative 4 over 3x. All right, so we're going to assume that x comma y have very large coordinates. All right, and basically what's going to happen here is that if you have that x and y are of course very large, then here's what happens. So look at y squared over 16. minus x squared over 9 equals 1, and then solve for y. Okay, well, first let's multiply by something to get rid of these fractions. So if we multiply through by 16, then the first fraction is gone. We get 16x squared over 9 is equal to 16. And then if we multiply through by 9, then we get 9y squared minus 16x squared is equal to 144. Okay, now if x and y are large, we can ignore this 144. Right? Because that 144 is going to be very small compared to our x and y. So all that's going to survive after a while are our x and y terms. Now, if we finish solving it, we get 9y squared is equal to 16x squared. Divide the 9 over. And then if we take the square root, we'll get y is plus or minus. The square root of 16 is 4. The square root of 9 is 3. And the square root of x squared is x. Right? So you're seeing that y is equal to x. Sorry, y is equal to plus or minus 4/3 x. And again, for large values of x, we can ignore the 144, and we see that it's going to be close to that line. One of those two lines, I should say. All right. Now for the foci of a hyperbola, you get sort of a similar situation as we did with the ellipse, right? So your foci of a hyperbola are 2 points such that if you pick any point on your hyperbola and you measure the distance from both of the foci and you add them, you're going to get the same number every time. All right, and you can find the foci similarly to as we did before, except it's always going to be 0 in the first coordinate. All right, so it will be 0 and then plus or minus a squared plus b squared. Okay, so if we find the two foci here in this example, all right, and again, I'm just going to do part C first, show that we have the two foci here. So in this case, we want square root of a squared plus b squared. So we want 16 plus 9, so square root of 25, so we get 5, of course, plus or minus. So 1 point that is a focus is 0, 5, and then 0, -5 is the other focus, and together they're the two foci. All right, so that's your part C. Now for part A, if we find a typical formula for the distance in terms of y, right? If we take our arbitrary point x comma y, then we have square root of x minus 0 squared, and then plus y minus 5 squared, which we can write as a square root of x squared plus y minus 5 squared. All right, and then of course, for part B, we could say the same thing, only now we're looking at -5, so minus a -5 would become a plus 5. So this is square root of x squared plus y plus 5 squared. All right, and that would be your distance from each of the two foci points to any arbitrary point. All right, so that concludes this video on quadratic functions and conics. I hope you enjoyed, and I will see you next time.